Next, let us find out the radius of the circle followed by the charged particle. We know when the velocity is perpendicular to the magnetic field, the magnetic force acts as the centripetal force which provides the circular path of the charged particle. Therefore, we can write centripetal force equal to magnetic force. In the first year, we have studied the equation for centripetal force, that is mv square by r. That is, when a particle of mass m moves with a speed of v along a circle having radius r, the centripetal force will be mv square by r. So putting that expression here, we can write mv square by r equal to magnetic force. We know the expression for magnetic force Q into V cross B. Therefore, we can write mv square by r equal to Q into V cross B. Or taking magnitude only, we can write mv square by r equal to QVB sin theta. In our case, theta is equal to 90 degree, that is the angle between velocity and magnetic field. It is 90 degree. Therefore, sin 90 is equal to 1. Therefore, we can rewrite the equation as mv square by r equal to QVB into 1. That is QVB itself. So, we need an expression for r. Then simplifying the steps, let us write mv by r is equal to qb. That is, by cancelling velocity v from both sides, or r is equal to mv by qb. But you know, m into v, mass into velocity, is momentum p. That is, r is equal to p, momentum p divided by qb. This is the expression for the radius of the circle followed by the charged particle. From this expression, it is clear that radius depends on mass and velocity directly, charge and magnetic field inversely. That is, for a charged particle having higher mass or higher velocity, the radius of the circle followed by it will be larger. Similarly, r is directly proportional to momentum, means greater the value of momentum, greater will be the radius of the circle followed by the charged particle. That is, r is the circle of the circle described by the charged particle. The larger the momentum, the larger is the radius and bigger the circle described. Next, let us find out the angular frequency of circular motion. We know the relation connecting angular frequency and linear velocity v. That is, v is equal to omega into r. This expression we have studied in the first year, that is for circular motion. Therefore, the angular frequency omega we can write v divided by r. But we know the value of radius r, already obtained that is mv divided by qb, r equal to mv divided by qb. Substituting here, we can write omega is equal to v divided by mv divided by qb. Simplifying, omega equal to qb divided by m. Next, frequency of circular motion. We know the connection between angular frequency and frequency. That is, omega is equal to 2 pi f. We have got the expression for angular frequency omega as qb divided by m. Therefore, instead of omega, we can put qb divided by m equal to 2 pi f, or qb divided by 2 pi m is equal to f. That is, expression for frequency is f equal to qb divided by 2 pi m. Looking this equation, we can see that frequency depends on charge q, magnetic field B, and mass of the charged particle m. It does not depend on velocity or energy. This independence of frequency from energy has important application in the design of cyclotron. The principle of cyclotron you will study later in this chapter. Next is time period of circular motion. Time period means it is the time taken for one revolution. It is the reciprocal of frequency. Therefore, time period T is equal to 1 by F equal to 1 divided by QB divided by 2 pi m. You will get T equal to 2 pi m divided by QB.